Welcome back. We're going to continue our studies of counting principles with the introduction of permutations. We're also going to look at permutation of elements R at a time. We'll explore distinguishable permutations, and we'll take a look at using RTI-84 to help us with these computations. First, let's define a permutation. In a permutation, an ordering of n elements is called a permutation of elements. So a permutation of n different elements is an ordering of the elements such that one element is first, one is second, one is third, and so on. So in permutations, order does matter. BAC is a different set from BCA, despite the same letters are being chosen for that particular set. So the number of permutations of n elements is given by the formula n times n minus 1, or essentially n factorial. In other words, there are n factorial different ways that a number of elements can be ordered. So let's explore finding the number of permutations. How many permutations of the letters A, B, C, D, and F can we come up with? Well, since we're doing permutations, we know there is no replacement. So once an item is taken out, we can't put it back in. And here we have 6 unique elements in our set. So if I set up 6 boxes for our elements to be placed in, essentially in our first box, there are 6 choices for the first choice. So we could choose an A, B, C, D, E, or an F. Let's say I just chose C for my first box. Well, now, since there's no replacement, I only have 5 choices. So if I choose E for my second box, now I only have 4 choices. And the next one, 3 choices, 2 choices, and finally the last one, only 1 choice. There are n factorial possibilities for each one. 6 times 5 times 4 times 3 times 2 times 1. This is the number of permutations of this particular set, or 6 factorial. Now let's explore permutations of elements R at a time. It's useful on occasion to order a subset of a collection of elements rather than the entire collection. For instance, you might want to order R elements out of a collection of n elements. Such as ordering is called a permutation of n elements taken R at a time. And that's given to us by this particular formula. The permutation P of n elements on the left is our subscript R at a time. For that, we'll use the formula n factorial over n minus R factorial. So let's say we have 8 horses running in a race. How many different ways can these horses come in first, second, and third? We don't care about all the races. Okay, we don't want to know the total number of permutations. We're not predicting 1 through 8 or anything like that, or just doing 8 factorial. What we're really looking for is a subset of 3 possibilities. How can they come in first, second, and third of our 8 events, or finishers? This is the permutation of 8. Essentially choose 3. So if we have a horse race, if Secretariat comes in first and Man of War comes in second and Seabiscuit comes in third, that's going to be a different ordering than, say, Seabiscuit coming in first, Secretariat coming in second, and Man of War coming in third. So those are different options. So this is a permutation of 8 choose 3. So on the left-hand side here, you can see what that looks like. And using our formula, that's 8 factorial over 8 minus 3 factorial, or 8 factorial divided by 5 factorials. So our 5 factorials cancel, and that's just 8 times 7 times 6, which is a total of 336. Another sample might be a coin club has 5 members. In how many ways can there be a president and a vice president? Our 5 members is our n, and our president and our vice president is kind of that choose 2, just a president and a vice president. Our r here is 2. It's a permutation of 5 choose 2. So you could look at it as we only have 2 spots, kind of like we did with the letters earlier, and there are 5 choices for the first one. Now there's no replacement. If you're going to be president, you can't also be vice president. So now there's only 4 choices left to be vice president, which is just 5 times 4 is 20. We could look at it using our formula, permutation of 5 choose 2, which is 5 factorial divided by 5 minus 2 factorial, 5 factorial over 3 factorial. So we get 5 times 4 times 3 factorial all over 3 factorial, and once again we get 20 different ways. Our third objective is to explore distinguishable permutations. Let's consider the set A, B, and C. The number of permutations here is 4 factorial. However, we can't distinguish which A is used and when it's used because there are multiple A's in the list. So we want to be able to distinguish the permutations. So the number of distinguishable permutations is given by n factorial, all divided by n1 factorial, n2 factorial, and 3 factorial, and so forth. What exactly does this mean? Let's take a look at a sample problem. In how many distinguishable ways can the letters in banana be written? Banana is a 6-letter word, but we have some duplicates. We've got 3 A's and 2 N's, and only 1 is B. So the number of distinguishable ways in which the letters can be written is 6 factorial, our total number of letters, divided by 3 factorial, which is our repeated A's, 2 factorial, which is our repeated N's, and then 1 factorial is all the other letters. By our formula, that's 6 factorial divided by 3 factorial divided by 2 factorial. The 3 factorials cancel, and 6 times 5 is 30, and 2 factorial and 4 simplify just to 2 over 1. 30 times 2 is 60. There are 60 different ways that can be written. So if you didn't follow that, we can do another sample. In how many distinguishable ways can the letters in mitosis be written? Well, mitosis has 7 total letters, so my numerator is going to be 7 factorial. And then there are 2 S's and 2 I's. For the S's and the I's, we have a 2 factorial and a 2 factorial. And of course, then everything else is just 1 factorial. I don't think we even need to write those down. We get 7 times 6 times 5 times 4 times 3 times 2 factorial all over 2 factorial times 2 factorial. So at least one of the 2 factorials simplify. And then I can probably simplify something like the 4 and the 2 to 2. And so we end up with 7 times 6 times 5 times 3 times 2, which I see here is 6 times 5 is 30, 60, 180 times 7, which gives me a grand total of 1,260 possibilities, or the distinguishable ways the letters could be written. In our final objective, we'll take a look at using our graphing calculator, our TI-84. And there is a feature on there for permutations of n choose r. So it calculates the number of permutations and elements taken r at a time. So I pull up my graphing calculator. We had an example earlier of the the president and the vice president out of a coin club of 5 members. So if I wanted to do that with my calculator, I can do the number of permutations. Well, I have a total of 5, so I've got to start with 5. So that's my n, and now I need to come up with the permutation command. So I go under the math menu. I've got some menus on the top. I want the probability, PRB. So I select PRB, and I've got step 2 here, NPR. I'll select 2. And now it was choose 2, 5, and my R was 2, so I choose 2, and I hit enter, and I get 20. In my horse racing example, I think I had 8, and probability. How many permutations could they? I hit the wrong thing. So I had 8 horses racing, and I want the number of permutations. NPR, and how can they finish in the top 3? 336. There's an example of how you can use your graphing calculator to answer permutation questions, and you'll get some more practice on permutations when I see you in class.